There is a speed that light travels at. You have probably heard the number before, and it is large enough that it stops feeling real. Light covers the distance between the Earth and the Moon in just over a second. But the strange part is not how fast that is. The strange part is that nothing has ever gone faster. Every object ever measured, every particle ever pushed to its limit, has fallen short of that speed. And the reason has nothing to do with our engines not being powerful enough. It goes much deeper than that. Pick up something heavy. Not in your imagination, actually feel the memory of it. A bag of groceries, a box carried upstairs. There is a moment, right at the start, before the thing is moving, where you feel everything pushing back. You lean into it, you apply force, and then, slowly, reluctantly, the object gives. That resistance is real. The object did not want to move, and once it was moving, it did not want to stop. You had to impose change on it, and the object resisted that change as though it had a preference. The heavier the object, the stronger that resistance. That relationship between mass and resistance is not a coincidence. It is a structural fact about what mass actually is. Mass is resistance to change in motion. When you push something, you are negotiating with that resistance. The object yields a little, accelerates, picks up speed, but something changes when objects move very fast. The resistance grows in a way that ordinary experience never prepared us for, and that quiet departure from the familiar is where this whole question begins. Why does it get harder to accelerate something the faster it already moves? What is doing the resisting? And why does that resistance eventually become something no force in the universe can overcome? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, share it with us in the comments. With that said, let's get back to the topic. The answer is not about friction or air resistance or anything pushing back from outside. It is something built into the fabric of what motion is, and it starts with what force actually does at high speed. Imagine you are pushing a box along a flat surface. No friction, no resistance from the ground, just you and the box and the force you apply. Every second you keep pushing, the box moves a little faster. The relationship is clean and simple. Double the force, double the acceleration. Push for twice as long, gain twice the speed. It feels mechanical, predictable, almost boring in how reliable it is. Now imagine that box is moving very fast. Not fast by everyday standards, fast by the standards of the universe. A significant fraction of the speed of light. You apply the same force. You expect the same result. But the box does not cooperate the way it used to. It accelerates, yes, but less than it should. You push harder. It still falls short of what the math used to promise. Something has changed, and nothing about the box looks different from the outside. This is where the first real crack appears in the intuitive picture of motion. At everyday speeds, the rules feel absolute. Force in, acceleration out. The equation is clean. But that equation is an approximation, a very good one, good enough that we built entire civilizations on it without noticing the error. At low speeds, the approximation is so accurate that the difference is unmeasurable. But as speed climbs toward a significant fraction of light speed, the approximation starts to fail. The gap between what the simple equation predicts and what actually happens begins to open up. What changes is the relationship between force and the resulting change in motion. At high speeds, the same force produces less acceleration than it did before, and the faster the object already moves, the more pronounced that shortfall becomes. Each increment of speed becomes harder to win than the last. You are not fighting air resistance or mechanical friction. You are fighting something that lives inside the object itself, something that grows as the speed grows. The natural question is, what exactly is growing? What property of the object is changing as it moves faster, given that the object itself seems unchanged? The box is still the same box. It has the same number of particles arranged the same way. Nothing has been added to it, and yet it responds to force as though it has become heavier. This is not a loose analogy. In a precise and measurable sense, the object behaves as though its mass is increasing. Physicists gave this a name, relativistic mass, though the name fell out of fashion because it can mislead. But the behavior is real, and it has been confirmed in particle accelerators many times over. Electrons pushed to high fractions of light speed require dramatically more energy to accelerate further than the simple prediction would suggest. The effect is not theoretical, it shows up in the measurements. So something about fast-moving objects makes them harder to accelerate. The resistance grows with speed, and that growing resistance is directly connected to the energy being poured into the object. The force you apply does not simply vanish, it goes somewhere, and where it goes is the next piece of this. Think about what it means to stop something that is already moving. A slow rolling ball is easy enough to catch. A fast one stings your hands. A faster one still could break a bone. The object has not changed. Its size, its shape, its composition, all the same. What has changed is how much of it there is to deal with, in a sense that is hard to put into ordinary words. Physicists call this momentum, and at everyday speeds it behaves exactly as you would expect. It scales with mass and it scales with speed, cleanly and proportionally. But momentum at very high speeds stops behaving that way. The clean proportionality breaks down. An object moving at a large fraction of light speed carries far more momentum than the simple multiplication of its mass and velocity would predict. And this is not a rounding error or a measurement artifact. It is a genuine departure from the familiar rule, and it deepens the faster the object moves. The reason matters because it reveals something about what momentum actually is at a fundamental level. At low speeds, momentum is essentially a measure of how much effort it would take to stop something or to change its direction. That effort scales in a simple way with mass and speed, but at high speeds, the relationship between speed and momentum becomes non-linear. Doubling the speed does not double the momentum. It increases it by more than that. And the closer the speed gets to light speed, the more dramatic that excess becomes. What this means practically is that to keep accelerating an object, you need to keep supplying force against a momentum that is growing faster than the speed itself is growing. You are not just fighting the inertia of a stationary object. You are fighting the accumulated momentum of an object that is already moving, and that momentum has become swollen beyond what its speed alone would suggest. There is a way to picture this without mathematics. Imagine each unit of speed you add to an object costs you a certain amount of effort. At low speeds, the cost per unit is roughly constant, but as speed climbs, each additional unit of speed costs more than the last. The price schedule is not linear. It curves upward, and it curves upward more and more steeply as you approach light speed. You are paying an ever-increasing price for an ever smaller gain. This curving price schedule is not arbitrary. It is a consequence of how energy and momentum are related at a deep level, a relationship that is baked into the geometry of the universe itself. And to understand why the price keeps climbing without limit, you have to look at what is actually happening to the energy you are pouring in. Because the energy does not simply become speed. At high velocities, it starts going somewhere else entirely. There is something deeply counterintuitive about what happens to energy at high speeds, and it is worth approaching slowly. At everyday velocities, the relationship between energy and speed feels straightforward. You apply force, the object accelerates, and the energy you put in shows up as motion. The faster the object moves, the more kinetic energy it carries. That energy is visible, measurable, and behaves exactly as you would expect. Pour in more energy, get more speed. The exchange rate feels fixed. But as an object approaches a meaningful fraction of light speed, that exchange rate begins to shift. You pour in energy, and the object does accelerate, but by less than it should. The energy went in. The speed came out. But the speed that came out was smaller than the energy that went in would have produced at lower velocities, and as the object moves faster still, the gap between energy invested and speed gained keeps widening. You are getting less and less speed back for every unit of energy you spend. This is not waste in the way that friction is waste. When friction bleeds energy away, that energy leaves the system as heat. You can account for it, measure it, point to where it went. What happens here is different. The energy stays inside the object. It has not leaked away. It is all still there. But it is no longer showing up as speed. It is showing up as something else, something that does not have an obvious name in everyday experience, but which has a very precise meaning in physics. The object is becoming harder to move, not because something external is resisting it, but because the energy already inside it is contributing to its resistance. Each increment of energy you add makes the object not just faster, but also more resistant to further acceleration. The energy feeds back into the very property that determines how difficult the object is to push, and that property is what we normally call mass. This is the first place where the intuitive picture of mass as a fixed, permanent quantity stamped onto an object at the factory starts to dissolve. Mass is not simply a label. It is a measure of something the object contains, and energy is part of what it contains. The faster the object moves, the more energy it carries, and the more of that energy folds back into its resistance to acceleration. The object does not grow in any physical sense. Its particles do not multiply, but its resistance to being pushed grows as though it has become heavier, because in a precise and measurable sense, it has. The practical consequence of this is stark. Each time you try to push the object a little faster, you are pushing against a resistance that has grown since the last time you pushed. The object you are accelerating now is not the same object, in terms of its resistance, as the one you started with. It has accumulated energy, and that energy is working against you. The faster it goes, the more energy it holds, and the more that energy resists your next push. You are always climbing a slope that is steepening beneath your feet, and this process has no natural stopping point from the inside. There is no mechanism within the object that says the resistance has reached its maximum. The resistance simply keeps growing as the energy keeps growing, which means the question of whether anything can ever reach light speed depends entirely on what happens to this resistance as you approach that boundary, and whether any finite amount of energy could ever be enough to get there. There is a number that sits at the center of modern physics, and most people have seen it written down without fully feeling what it means. Energy equals mass times the speed of light squared. It appears on posters and t-shirts and the covers of popular science books, and familiarity has made it feel almost decorative. But underneath the familiarity is something genuinely strange, and it is worth slowing down to let it land properly. What the equation says, in plain terms, is that mass and energy are not two different things that happen to be related. They are the same thing expressed in different forms. Mass is condensed energy. Energy is liberated mass. The speed of light squared is simply the conversion factor between the two, a very large number, which is why a small amount of mass contains an enormous amount of energy, and why it takes an enormous amount of energy to produce even a small change in how a fast-moving object behaves. Now bring that back to the object being accelerated. At rest, the object has a certain mass, a certain amount of energy locked inside it in its most compressed form. When you begin pushing it, you add energy to the system. At low speeds, almost all of that added energy shows up as kinetic energy, as motion. The object moves faster, and the amount of energy folded back into its mass-like resistance is negligible. The conversion is so small at everyday speeds that it never shows up in any measurement you could make with ordinary tools. But at high speeds, the situation changes. The energy you are adding is no longer going predominantly into motion. A growing portion of it is folding into the object's resistance, behaving in every measurable way like additional mass. The object is not just moving faster, it is also becoming, in a functional sense, heavier. And because mass determines how much force is needed to produce a given acceleration, the object now requires more force than it did before to achieve the same result. This feedback loop is the core of why light speed is unreachable. Every push you give the object adds energy. That energy partly becomes speed and partly becomes additional resistance. The faster the object moves, the larger the fraction of new energy that folds into resistance rather than speed. The proportion keeps shifting in the wrong direction. You are running a race where the track lengthens every time you take a step. And crucially, this is not a gradual inconvenience that eventually plateaus. The mathematics describes a curve that steepens continuously as speed approaches light speed. The resistance does not approach some large but finite maximum. It grows without bound. As the object's speed approaches light speed, the energy required to push it even slightly faster approaches infinity. There is no clever workaround, no more efficient engine, no better angle of attack. The structure of the relationship between energy and resistance makes it categorically impossible to reach light speed with any finite energy input, which raises a question that the energy picture alone cannot fully answer. Why does this curve have the shape it does? Why does resistance grow in this particular way, following this particular mathematical form, rather than some other? The answer to that requires stepping back from the object entirely and looking at the space and time it is moving through, because the resistance is not really a property of the object. It is a property of the geometry the object exists inside. There is a temptation, when thinking about mass and energy being equivalent, to treat it as a poetic statement, a beautiful symmetry, a satisfying unification of two concepts that used to seem separate. But the equivalence is not poetic, it is operational. It shows up in measurements. It has consequences that are strange enough to be worth sitting with carefully before moving on. Consider what it means for an object to have mass at all. Before any of this, mass felt like a simple property, something an object just had, the way it has a color or a shape. You weigh the object, you get a number, and that number is its mass. Fixed, permanent, independent of what the object is doing or where it is going. That picture is accurate enough for everyday life that nothing ever forces you to question it. But the equivalence of mass and energy quietly dismantles that picture. If energy and mass are the same thing in different forms, then the mass of an object is not just a count of its particles. It is a measure of the total energy content of the object in its rest state. The particles themselves are concentrations of energy. The bonds between them carry energy. The internal motion of their components carries energy. All of it contributes to what registers on a scale as mass. This means mass is not a fixed label. It is a running total, and that total can change. When you heat an object, you add energy to it, and its mass increases by a tiny amount, so small at ordinary temperatures that no scale could detect it, but real nonetheless. When a nuclear reaction releases energy, the products have slightly less mass than the original materials because some of the energy content has left the system. The mass did not disappear. It converted. It left in the form of radiation, of light, of kinetic energy in the expelled particles. Now return to the accelerating object. As you push it faster, you are adding energy to it. That energy has to go somewhere, and it does not all go into speed. A portion of it settles into the object as additional energy content, additional mass, in the most literal sense of that word. The object's resistance to further acceleration grows because the object now contains more energy than it did before you pushed it. You have, in a precise sense, made it heavier by accelerating it. This is why the resistance curve steepens without limit. Each push adds energy. Each addition of energy increases the mass-like resistance. Each increase in resistance makes the next push less effective. The cycle tightens as speed increases, because the fraction of new energy that converts into resistance rather than speed grows larger the closer the object gets to light speed. At the limit itself, every joule of energy you add would convert entirely into resistance, with nothing left over to produce additional speed. The object would absorb energy indefinitely and never move faster. But this still leaves a deeper question open. Why does energy behave this way? Why does it fold into resistance rather than speed as velocity increases? The answer requires understanding something about the structure of space and time that is easy to state but takes a moment to truly absorb. Space and time are not separate containers that the universe happens to exist inside. They are woven together into a single structure, and the way objects move through that structure is what determines everything we have been describing. There is a way of thinking about space and time that most people carry around without ever examining it. Space is where things are. Time is when things happen. Space has 3 dimensions. You can move left or right, forward or backward, up or down. Time has 1 dimension. It moves forward steadily at the same rate for everyone, regardless of what they are doing or where they are going. That picture feels so natural that it is difficult to imagine what questioning it would even mean. But that picture is wrong. Not approximately wrong in the way that a map is a simplification of a landscape. Wrong in a way that changes the answer to almost every deep question about motion, energy, and the structure of reality. Space and time are not separate. They are 2 aspects of a single 4-dimensional structure, and that structure has a geometry, a set of rules about distances and relationships that governs everything moving within it. The name for this structure is space-time. It was not invented as a philosophical convenience. It emerged from the mathematics of electromagnetism and the behavior of light, and it was made precise by Einstein in the early 20th century. But the important thing is not the history. The important thing is what the structure implies for anything moving through it. In ordinary geometry, the distance between 2 points is fixed. You can measure it, and no matter what path you take between those points, the underlying distance does not change. Space-time has an analogous concept, a kind of distance that combines separation in space with separation in time. Physicists call it the space-time interval, and this interval, unlike ordinary distance, behaves in a way that feels deeply strange at first. When you move through space, your movement through time changes. When you move through time, your movement through space is affected. The two are coupled. They trade off against each other in a way that is governed by a fixed relationship, a relationship that involves the speed of light as a conversion factor between the spatial and temporal parts of the interval. This coupling is not a metaphor, it is measurable. Clocks on fast-moving spacecraft run slower than clocks on the ground. This has been confirmed with atomic clocks on aeroplanes, with particles in accelerators, with satellites whose timing signals have to be corrected for exactly this effect. The coupling between space and time is real, and it has practical consequences that engineers account for every day. What this means for an accelerating object is that motion through space and motion through time are not independent quantities you can adjust separately. They are parts of a single motion through a single structure, and that single structure imposes a constraint that no force, no engine, and no amount of energy can escape. The constraint is not a rule written into the physics from outside, it is the geometry itself. And the next step is to see exactly what that geometry demands of anything moving through it. Here is something that takes a moment to settle into, but once it does, it reframes everything that came before. Every object in the universe is always moving through space-time, not just objects that are visibly traveling, rockets, planets, speeding particles. Every object, including ones that appear completely still, including you, right now, lying there, not moving through space at all. The reason is that space-time has 4 dimensions, and motion through it means motion through all 4. 3 of those dimensions are spatial, the 4th is time, and time is always passing. Even for an object that is perfectly stationary in space, time is moving forward, and that forward movement through time counts as movement through space-time. You are always in motion, you cannot opt out of it. Now here is the part that carries real weight. The speed at which everything moves through space-time is fixed, not approximately fixed, not fixed under normal conditions, fixed absolutely without exception for every object in the universe regardless of its mass, its composition, or its history. Everything moves through space-time at exactly the speed of light. That statement sounds wrong at first, because you are clearly not moving at the speed of light. You are lying still. But the speed of light here is the combined speed through all 4 dimensions, through space and through time together. When you are stationary in space, your entire space-time speed is directed through time. You are moving through time at the maximum rate and through space not at all. The full quota of your space-time motion is being spent on moving through time. When you begin moving through space, something has to give. Your total space-time speed remains fixed at light speed. So as your spatial speed increases, your rate of movement through time must decrease to compensate. The two trade off against each other, held in balance by the fixed total. More speed through space means less speed through time. The ledger always balances, and the total never changes. This is not an abstract bookkeeping exercise. The reduction in movement through time is exactly what we measure as time dilation. Clocks on fast-moving objects run slower, not because the clocks are affected by motion in some mechanical sense, but because the objects genuinely are moving through time more slowly. They have redirected some of their time motion into space motion, and as a result they age more slowly, their internal processes run more slowly, their clocks tick more slowly. The geometry of space-time is producing a real physical effect, And this reframes the question of acceleration entirely. When you push an object and make it move faster through space, you are not simply adding motion to something that was sitting still. You are rotating its motion within space-time, tilting it away from the time direction and toward the space direction. The total motion stays fixed, the direction shifts, and the resistance you feel when you try to push a fast-moving object is, at a deep level, the resistance of that rotation, the geometric stubbornness of a four-dimensional structure that will not let you exceed its fixed total. Carry that picture forward for a moment. Every object has a fixed total speed through space-time, always equal to the speed of light, always, and that total is divided between movement through space and movement through time. When an object is stationary in space, all of its space-time speed flows through time. When it begins moving through space, the time component shrinks to make room. The two are always in balance, always summing to the same fixed total. Now think about what happens as an object accelerates. Each time you push it, you are redirecting a little more of its space-time motion away from the time direction and toward the space direction. Early on, when the object is moving slowly, this redirection is easy. There is a large reservoir of time motion available to convert. The object has plenty of space-time speed still flowing through time, and nudging some of it into the spatial direction costs relatively little. The geometry is accommodating, and the object responds to force in the familiar, predictable way. But as the object moves faster through space, the reservoir shrinks. More and more of its fixed space-time speed has already been redirected into spatial motion. Less and less remains in the time direction, and redirecting what remains becomes progressively harder, not because of anything changing inside the object in an ordinary physical sense, but because the geometry of the reallocation becomes increasingly resistant. You are trying to tilt a motion that is already heavily tilted, and each additional degree of tilt requires more effort than the last. This is why the energy cost of acceleration curves upward so steeply as speed increases. It is not that the universe is applying some external brake. It is that the internal geometry of how motion is distributed across space-time dimensions makes each increment of spatial speed more expensive than the one before. The mathematics of that geometry produces exactly the curve we see in particle accelerators, the curve where energy requirements rise sharply and without limit as speed approaches light speed. There's a way to feel the endpoint of this process intuitively. Imagine an object that has redirected all of its space-time motion into the spatial direction, nothing flowing through time, everything flowing through space. That object would be moving through space at the full fixed total, at light speed, and it would have zero motion left to give to time. Its clock would not tick, its internal processes would not advance. From its own perspective, no time would pass at all. But to reach that state from a standing start, you would have to redirect every last unit of time motion into spatial motion, and the geometry of space-time makes that final redirection infinitely resistant. As the time component approaches zero, the effort required to reduce it further approaches infinity. You can push the time component smaller and smaller, spending more and more energy with each push, but you can never reach zero. The geometry will not allow it. The end point is always just out of reach, receding as you approach it, in the same way that a mathematical limit can be approached but never touched. This means the barrier to light speed is not a wall you crash into. It is a horizon that retreats. Every increment of energy moves you closer, but the cost of the next increment always exceeds the last, and the increments needed to close the remaining gap always outnumber the energy you have available. The speed of light is not a speed you fail to reach because you run out of fuel. It is a speed the geometry of space-time makes structurally unreachable for anything that starts with time motion to spend. There is a moment in understanding time dilation where it stops feeling like a clever trick and starts feeling like something unavoidable. That moment usually comes when you stop thinking of time as a backdrop, a passive stage that events play out on, and start thinking of it as a dimension that objects move through, the same way they move through space. Once that shift happens, time dilation does not need to be explained. It falls out of the geometry on its own. Return to the object moving through space-time at its fixed total speed. When it is stationary in space, all of that speed flows through time. The object ages at the maximum possible rate. Its internal processes, every chemical reaction, every electrical signal, every oscillation of every atom, all run at full speed because all of the object's space-time motion is being expressed as movement through time. Time, for that object, is passing as fast as it ever can. Now, the object begins moving through space. Some of its space-time speed shifts from the time direction into the space direction. The total stays fixed, but the distribution changes, and because less of the object's motion is now flowing through time, time passes more slowly for it. Its internal processes slow down. Its atoms oscillate less frequently. Its clocks tick fewer times per second. Not because anything has physically interfered with the clock mechanism. The clock is working perfectly. But because the object itself is genuinely moving through time more slowly than it was before. This is the part that tends to feel strange. The slowing is not an illusion. It is not a perspective effect that cancels out when you compare notes. A clock that has been moving fast and then returns to rest will show fewer elapsed seconds than a clock that stayed still. The difference is real and permanent. The moving clock genuinely experienced less time because it was genuinely moving through time more slowly, because a portion of its fixed space-time speed was directed through space instead. The faster the object moves through space, the more pronounced this effect becomes. At everyday speeds, the fraction of space-time motion redirected into space is so small that the resulting time dilation is completely unmeasurable without extremely precise instruments. But it is there. The atomic clocks aboard fast-moving aircraft lose a measurable number of nanoseconds compared to identical clocks on the ground, and the amount they lose matches the prediction from the geometry exactly. At speeds approaching light speed, the effect becomes dramatic. A particle accelerated to 99% of light speed ages far more slowly than a stationary particle. At 99.9%, the slowing is more extreme still. As the speed approaches light speed itself, the time dilation approaches its absolute limit, a state in which time for the moving object slows towards zero. The object's internal processes would approach a complete standstill. From the perspective of the outside universe, the object would appear almost frozen in time, its clock barely ticking, its processes nearly suspended. And this connects directly back to the energy cost of acceleration. Every push that redirects more space-time motion into the spatial direction also slows the object's time further. The two effects are the same effect, viewed from different angles. The growing resistance to acceleration and the slowing of time are both expressions of the same geometric reality, that the object's fixed space-time speed is being tilted further and further from the time direction, and that each additional degree of tilt extracts a higher cost from the geometry. The resistance and the time dilation are not two separate phenomena. They are one phenomenon, and it lives in the structure of space-time itself. Picture the object now moving at a very large fraction of light speed. Not a comfortable cruising speed, something extreme. 95% of light speed. 99%. 99.9. Each of those steps represents an enormous investment of energy, far beyond what the simple intuition of adding speed would suggest. And yet each step leaves the object still short of light speed by a gap that feels, from the outside, like it should be closable with just a little more effort. That feeling is the geometry being deceptive. The gap, in ordinary speed terms, does look small. At 99% of light speed, the remaining 1% seems almost trivial. But the energy required to close that 1% is not 1% of the total energy spent so far. It is vastly more. The curve of energy cost has been steepening the entire time, and at 99% it is nearly vertical. The energy needed to push from 99% to 99.1% exceeds what was needed to accelerate from rest to 99% in the first place. The numbers become almost incomprehensible. At 99.9% of light speed, the situation is more extreme still. The object's clock is ticking at a fraction of the rate of a stationary clock. Its internal processes are running in what would appear, from the outside, to be extreme slow motion. The energy already contained in its motion is staggering, far beyond anything that could be produced by any fuel source we know of, even in principle, for any object with meaningful mass. And yet the geometry still places light speed ahead of it, unreachable, receding at the same rate the object approaches. What is happening physically during this approach is worth describing carefully. The object's space-time motion is now almost entirely directed through space. The time component has been compressed to a tiny fraction of its original value. The total is still fixed at light speed. That never changes. But the distribution is now extreme. Almost everything is spatial. Almost nothing is temporal. The object is threading its motion almost entirely through space, and time has been squeezed to nearly nothing. To go further requires compressing the time component even more. But the time component is already close to zero, and the geometric resistance to compressing it further is enormous. Each additional unit of spatial speed requires the time component to give up a little more, and the resistance to that giving up grows as the time component shrinks. The geometry behaves like a material that becomes stiffer the more you compress it, and unlike ordinary materials, this one has no yield point. It does not eventually give way. It simply keeps stiffening without limit, all the way down to zero. This means the object can approach light speed indefinitely. There is no point at which the geometry snaps and the object breaks through to a higher speed. There is no threshold beyond which the rules change. The resistance simply continues to grow, smoothly and without interruption, for as long as energy is supplied. The object gets closer and closer to light speed, and the universe accommodates that approach, but it never accommodates arrival. Light speed is not a barrier in the sense of a wall. It is a limit in the mathematical sense, a value that a function can approach arbitrarily closely but never equal, no matter how large the input becomes. Set aside the object for a moment and think about the energy side of this from a clean starting point. To accelerate any object with mass from rest to a given speed, you need to supply energy. At low speeds, the amount of energy required is modest and scales in a simple, predictable way with the mass of the object and the square of its speed. Double the speed, quadruple the energy. That relationship feels clean and manageable, and it holds well enough for everything from thrown balls to spacecraft leaving Earth's atmosphere. But that clean relationship is an approximation, and it begins to fail as speed increases. The precise relationship, the one that matches every measurement ever made, describes an energy requirement that does not simply scale with speed squared. It scales with a factor that grows as speed increases, and that factor has a specific mathematical form. As speed approaches light speed, that factor does not approach some large but finite number. It grows without bound, it diverges, it heads toward infinity. What that means in practical terms is this. Suppose you wanted to accelerate a single object with the mass of a grain of sand to 99% of light speed. The energy required would already be extraordinary, comparable to the energy released by a large nuclear weapon. To push that same grain of sand to 99.9% would require roughly 10 times more energy still. To reach 99.99%, 10 times more again. Each additional 9 you add to that percentage multiplies the energy requirement by a large factor, and the 9s can keep being added forever, with the energy requirement growing each time, while light speed itself remains perpetually ahead. To actually reach light speed, not approach it, but reach it, the factor in that energy equation would have to become infinite energy, applied to even the smallest object with any mass at all. And infinite energy is not a practical limitation in the way that running out of rocket fuel is a practical limitation. It is a categorical impossibility. There is no configuration of matter and energy in the universe that constitutes an infinite energy source. The total energy content of the observable universe is large, but it is finite, and finite energy applied to a massive object produces a speed that is always provably less than light speed. This is the point where the question shifts from being about engineering to being about mathematics. The impossibility of reaching light speed is not the same kind of impossibility as building a perpetual motion machine, where the engineering is simply too difficult. It is the same kind of impossibility as dividing a number by 0. The mathematical structure of the relationship between energy and speed for a massive object simply does not contain light speed as an achievable value. It is outside the domain of the function. The function produces a real finite speed for any finite energy input, and that speed is always less than light speed. Light speed itself corresponds to an infinite input, which is not a real number, and therefore not a physically meaningful quantity. This is also why no loophole exists in the form of a sufficiently advanced propulsion system. The limitation does not arise from how the force is applied, or what fuel is used, or how efficiently the engine converts energy into thrust. It arises from the mathematical relationship between energy, mass, and speed, a relationship that is the same regardless of how the energy is delivered. A perfectly efficient engine, one that converted its fuel into thrust with no losses whatsoever, would still face the same diverging energy requirement. The efficiency of the process is irrelevant. The structure of the mathematics is the constraint, and no engineering can reach outside the mathematics. Everything described so far has been about objects with mass, grains of sand, electrons, spacecraft, boxes being pushed across frictionless surfaces. All of them share the same property. They have mass, and that mass is what makes light speed unreachable for them. The energy requirement diverges. The geometric resistance grows without limit. The time component of their space-time motion can be compressed, but never eliminated. Mass is the thing that keeps them on the wrong side of the limit, but light itself reaches that limit. Light travels at exactly light speed, always, without exception, through any vacuum. It does not approach light speed the way an accelerating particle does, getting closer and closer while never quite arriving. It simply moves at that speed from the moment it exists, and it does this without any engine, without any fuel, without any force being applied to it. So what is different about light? What does it have or lack that allows it to do what no massive object can? The answer is that light has no mass. A photon, the particle that light is made of, has zero rest mass. And that single fact changes everything about how it relates to the geometry of space-time. Recall the picture of every object moving through space-time at a fixed total speed, with that total divided between spatial motion and temporal motion. For a massive object, there is always some minimum amount of temporal motion that cannot be redirected into spatial motion, no matter how much energy you supply. The mass of the object is what enforces that minimum. It is what keeps the time component from reaching zero. A massless particle has no such minimum. There is no mass to enforce a floor on the time component. The time component can go all the way to zero. And when it does, the entire fixed space-time speed is directed through space. The particle moves through space at the full fixed total, at light speed, and moves through time not at all. From the photon's perspective, if such a perspective could exist, no time passes between its creation and its absorption. The journey, however long it appears to outside observers, takes zero time for the photon itself. It exists at one moment and then at the next, with nothing in between. This also explains why light cannot travel slower than light speed through a vacuum, which is a less commonly asked but equally interesting question. A massive object can be at rest. It can move slowly. It has the option of directing its space-time motion into the time dimension rather than the space dimension, because its mass allows it to have temporal motion without spatial motion. A massless particle has no such option. With zero mass, there is nothing to anchor it to the time dimension. It must direct all of its space-time motion into space. It has no mechanism for moving through time while remaining still in space. Light speed is not a speed that light chooses. It is the only speed that a massless particle can have, given the geometry it exists inside. This draws a clean line between two categories of things in the universe: things with mass, which must always move slower than light, for which light speed is an unreachable limit requiring infinite energy, and things without mass, which must always move at exactly light speed, for which any other speed is geometrically impossible. The speed of light is not simply a fast speed that massive things fail to reach and massless things happen to achieve. It is the dividing line between two fundamentally different relationships with space-time, and everything in the universe falls on one side of it or the other. There is something about light that tends to get mentioned in passing without being given the weight it deserves. The speed of light is the same for every observer, regardless of how fast they are moving. Not approximately the same, not the same after you account for certain corrections. Exactly the same, measured identically by every measuring device in any state of motion anywhere in the universe. And that fact, which sounds at first like a minor technical detail, is actually one of the strangest and most structurally important features of reality. Think about what happens with ordinary speeds. If you are standing on a platform and a train passes you at 100 kilometers per hour, and someone on the train throws a ball forward at 50 kilometers per hour relative to the train, you see the ball moving at 150 kilometers per hour. The speeds add. That is so deeply intuitive that it barely registers as a rule. It just seems like arithmetic. Of course they add. What else would they do? Now replace the ball with a beam of light. The train is moving at a large fraction of light speed. Someone on the train shines a torch forward. You would expect, by the same arithmetic, to measure the light moving faster than light speed plus the speed of the train. But that is not what happens. You measure the light moving at exactly light speed. The person on the train also measures it at exactly light speed. Every observer, in every state of motion, measures the same beam of light moving at the same speed. The speeds do not add. The arithmetic that works for balls and trains simply does not apply to light. This is not an experimental anomaly that physicists are still trying to explain. It is a foundational feature of how space-time is structured, and it has been confirmed by every precision measurement ever attempted. The reason it holds is precisely because of everything described in the preceding segments. Space and time are not separate and independent. They are coupled dimensions of a single structure, and that coupling is governed by a fixed conversion factor, the speed of light. When an observer moves, their measurements of space and time both shift in exactly the way needed to keep the speed of light constant. The geometry compensates automatically. It is not a coincidence. It is a consequence of the structure. What this means is that the speed of light is not just a speed. It is a structural constant of space-time itself. It is the rate at which the spatial and temporal dimensions of the universe convert into each other. It is embedded in the geometry at a level more fundamental than any physical law, because physical laws themselves are written in the language of that geometry. When physicists write equations describing how particles move, how fields behave, how energy transforms, all of those equations inherit the speed of light as a fixed feature of the space they are written in. It cannot be engineered around because it is not an engineering constraint. It is a geometric one. And this is why the same speed appears in the equation connecting mass and energy. The speed of light squared in that equation is not there because light happens to be involved in the conversion between mass and energy. It is there because the speed of light is the conversion factor between the spatial and temporal dimensions of space-time, and mass and energy are themselves expressions of those dimensions. Everything connects back to the same underlying geometry. The constant speed of light, the impossibility of faster-than-light travel, the equivalence of mass and energy, the reality of time dilation. These are not separate discoveries that happen to be consistent with each other. They are different faces of a single geometric fact about the structure of the universe. There is one final way to understand why nothing travels faster than light, and it is the deepest of all the ways considered so far. Not deeper in the sense of being more mathematical, but deeper in the sense of being more fundamental, closer to the bedrock of what the universe is and how it holds together. It has to do with causality, with the simple, quiet fact that causes happen before their effects. Causality feels obvious to the point of being barely worth stating. A rock hits a window and the window breaks. The hitting comes first. The breaking comes after. That sequence is not negotiable. You cannot have the window break before the rock arrives. The order of events is fixed, and the universe enforces it without exception in every situation, for every observer who has ever made a measurement. Cause precedes effect, always. Now consider what would happen if something could travel faster than light. Not just slightly faster, genuinely, arbitrarily faster. In a universe where space-time has the geometry it has, where space and time are coupled dimensions governed by a fixed conversion factor, faster than light travel does not just mean moving quickly. It means something far more destabilizing. Because of how space and time trade off against each other for different observers, a signal or object moving faster than light in one observer's frame of reference would, from another observer's frame of reference, be moving backward in time. The mathematics of the geometry makes this unavoidable. Faster than light travel and backward time travel are not separate speculative ideas. In the geometry of space-time, they are the same idea, and backward time travel breaks causality. If a signal can travel backward in time, then effects can precede their causes. A message could arrive before it was sent. A window could shatter before the rock left the hand. The universe would lose the property that makes sequences of events meaningful, the property that allows one thing to reliably follow from another. Physics, in the deepest sense, would become incoherent. The equations that describe how systems evolve forward in time depend on causality being intact. Remove it, and the framework that makes prediction possible dissolves. So the speed of light is not just a limit on how fast objects can move. It is the boundary that separates the causal structure of the universe from incoherence. Everything inside that boundary, every signal, every interaction, every transfer of energy or information, preserves causality. Effects follow causes. Sequences are consistent across all observers. The universe remains a place where the past reliably produces the future. The speed of light is the outermost edge of that region of consistency. Beyond it, the geometry of space-time offers no guarantee that time flows in any particular direction, and causality, the quiet assumption underlying every physical law ever written, comes apart. This is why the limit feels so absolute. It is not a rule imposed on the universe from outside, the way a speed limit is imposed on a road. It is not a consequence of our current technology being insufficient. It is not a gap in our understanding that a future theory might close. It is the shape of causality itself, written into the geometry of space-time at the most fundamental level accessible to physics. The universe is structured so that causes precede effects, and the speed of light is precisely the speed at which that structure holds together. To exceed it would not be to travel fast. It would be to exit the coherent universe entirely. Everything in this chain of reasoning started with something almost embarrassingly simple: the feeling of pushing a heavy object and sensing it push back. That resistance followed all the way down through energy, through mass, through the geometry of space-time, through time dilation, through the nature of light itself, leads here. To the realization that the universe has a shape, and that shape has a speed, and that speed is not a ceiling someone drew on a diagram. It is the outermost boundary of everything that can coherently exist, interact, and cause.